Hello, my name is Peter Anzadeo, and this is the fourth lab for Physics 1 at Georgia Tech on oscillations. So, what is the purpose of this lab? We are looking into the concept of oscillations, specifically with regards to a spring mass system. Ultimately, we want to compare and contrast the observational data from a physical oscillation from a video recorded and a computational model which we've created to better understand the concept. The fundamental physical principles behind this concept are oscillations, obviously, as well as the spring force and the force of gravity on Earth, and everything that is encompassed by the energy principle. The two models used in this lab are the video that we are using in Tracker, and the computational model we've created in GlowScript. The preview of the result. So the model proved to be relatively accurate, and in the end, the energy principle was upheld throughout the oscillations. So here are the main physics ideas behind this lab. Obviously, we have the usual derivation for Newton's second law, giving us the velocity update formula and the position update formula, dividing everything by m from the momentum update formula to the velocity update formula, and plugging this in for the average to update position. And then we're introducing the force of gravity on Earth, the spring force, which come into play as potential energy for the energy principle. And so for delta E, we have kinetic energy for this problem, which is 1/2 mv squared. And then for delta U, we have potential gravitational energy and potential spring energy. And those are the only two for this problem. And since we are considering everything regarding this problem in the system, essentially the surroundings do no work, so this goes to 0. And here's the lab. The origin is at the axis of which the spring is connected to. And then we can see the initial conditions as to where the spring mass starts at in the video. And then, as this kind of shows here, the track goes in this circular oscillation. And so, as I said, the system is a spring mass at Earth, and we consider the surroundings as essentially negligible. So here are the results / conclusions. So shown on the right, the computational model proved to be relatively accurate of the experiment. For some reason, probably some error, as the model does not take into consideration things as air drag, stuff that we are considering negligible. And so it's slightly off, but it exhibits the same, wave-like oscillation pattern. It's just a little bit off. And so what does this mean? The energy principle is satisfied, because as we look at this graph here in the bottom right, we see that throughout the entire time, delta E, total energy, remains 0, as basically shown here from the energy principle. Additionally, we see that the gravitational spring energy and the gravitational energy due to gravity exhibit the same path, but in the opposite phase, essentially. And then delta K is exhibiting a wave-like function. But what's essential is that the total energy, delta E, always remains 0. And so for estimating the period of oscillation, I ended up getting the same period, about, more or less, for both methods, which proved to be about 1.519 seconds. And here's a little visual of the spring mass oscillation from the computational model at the end of its runtime. The blue represents the computational model, and you can see the path that it took, and the red ball here represents the actual experiment, and you can see, as shown over here, it's just off by a tiny bit. So yeah, that's it, and thank you.